thanks a lot, and thank you very much for this opportunity. First of all, I should maybe apologize for all the compromises I need to do to keep up this hybrid format. But in case there are any problems, just let me know. So first compromise is between my background and my lighting, and I chose for lighting, as you obviously see. So I hope now you can see my screen.
Yes, very well. Can everybody see? Okay. Okay, then it's my pleasure to introduce our first speaker of today, J.Lukkarinen from the University of Helsinki, and he will speak about pre-thermalization in a classical phonon field, slow relaxation of the number of photons. Thank you,
Thank you very much. So I will be happy to take questions if it's possible. So the topic is maybe a bit off for this audience, but I hope. So the main reason is that it's not completely mathematically rigorous. However, I myself found these properties, even though they are backed up mainly by numerical work, quite intriguing. So, and I would like to start by sharing them also with you. And hopefully after, I don't know, not maybe after this workshop, but very quickly afterwards, we will have proofs as well. So the topic is pre-thermalization. I will explain in a bit more detail for those who have never heard of this concept. I was not familiar with it either a couple of years back. But mainly, this is an example of that in a context which is hopefully more familiar to everybody. So that's a standard classical discrete Hamiltonian system which corresponds to phonons or is motivated by phonons. The work here I'm talking about is very much in collaboration with François Huffeners. In fact, he's the one who did all the hard work for the simulations. And but in addition, I'm also relying on previous results with Herbert Phon and Kenichiro Aoki on these systems, as well as on previous simulations and work by Christian Mendel and Jean-Fen Lu. So I wanted to start by recalling things which everybody might be already familiar with, but in any case, one of the purposes here is to really fix my model, the system I'm going to talk about, as well as some basic background notions of what I mean when I talk about kinetic theory of phonons. And if you are curious about details here, so there will be zero details. First of all, it's not only non-mathematical here, it's also impossible to follow unless you fix some of the details, but at least there's an archive link, which you hopefully will be able to find out. It's a chapter in a certain lecture notes in physics, but this archive link will give the part corresponding to my text. And a couple of notations, because I always feel that these are not totally standard, so therefore I have to explain to avoid many questions right in the beginning. First of all, I'm going to talk about systems which in some sense are very simple, at least on the level that they are easy to define or easy to show that they are well defined. So I'm starting with finite lattices, systems which have finitely many particles. A notation lambda will be used for the labels of the particles. There will be a corresponding dual lattice and Fourier transform defined here. And just to point out a couple of things which otherwise might be mysterious. So 2 pi's are in the exponent. I have a minus sign there. And this notation will be very convenient later on. This is a notation which looks like an integral. In principle, it's integral over measure, but in fact, it corresponds to finite sum. So there are no questions about regularity or well-definedness when I'm using these objects. There will also be something appearing later on, which looks like Dirac delta. Again, for finite lattices, this is a perfectly well-defined function. It's a function which takes wave numbers k, a modulo 1, and if they are 0, it produces a huge number corresponding to the size of the lattice. Okay, those were my notations, but let's go now to the system I want to talk about. So these are not exactly Fermi-Pascal-Olam-Jingjiao chains, they are sort of inspired by them. So the main difference here is that I'm going to look at so-called on-site perturbations, on-site unharmonicities, whereas in the original model these were depending on the displacements, or sorry, on the differences between the particle positions. A couple of important parameters to remember for the later. So there are 3 parameters which will appear throughout the talk. The one which is most obvious is the coupling constant of the unharmonic term relative to the harmonic term, and overall scale here is 1. It's because it's essentially determined by these 1/2s here. I will consider 2 different types of perturbations. So these are, for the coming results, we'll get 2 different values. The most common one, which we studied also earlier with Heberspohl and Kinetic, it corresponds to the lowest non-trivial one. So we want them to be even for stability reasons, but so the lowest non-trivial one is 4. But also some results are done for potentials of order 6, just to test whether the predictions can be transported, also whether they make sense, let's say. So you have most of the time when you see potentials and R's, they are 4, but every once in a while there will be a couple of places where it's also 6. The coupling constant lambda is non-negative, but one important parameter which often is not highlighted here is related to the harmonic coupling. This is the parameter delta here. For stability reasons, it has to have an absolute value less than or equal to 1/2. The negative values can be easily transformed so that we study only the positive case. So in principle, and also we don't want to study here 0 here because that would have no harmonic interaction. So we want to have a case where we have when lambda is 0, that we have a well-defined model with some non-trivial interactions. And it is essentially dictates that this parameter has to be between 0 and 1/2. And for technical reasons, which I guess nobody will have time to look at during the talk, I'm also going to take out the possibility of so-called unpinned models. So cases where there is no harmonic pinning potential. So that corresponds to the delta parameter 1/2. So that's the Hamiltonian function, and this as such is just a function of these finite vectors p and q. But next we look at the dynamics, and I said to call it Hamiltonian. So the dynamics are generated using the standard definitions by the function h on the previous slide. But again, my notation to fix notations, I'm going to use Poisson bracket notation quite a lot, and just to point out that's the order in which I wanted to define it. With this particular order, so these are then the corresponding evolution equation for these basic canonical variables q and p. As usual for these classical Hamiltonian systems, the derivative of q is all proportional to p. I'm normalized my system so that this is the case, and then there is this minus sign, which gives the forced. So when lambda is not 0, if r is 4 or 6, the evolution equations are nonlinear. So no obvious way of how to solve them in any sort of closed form. However, the dynamics are still well defined, especially in particular for these even integer values. This comes from the fact that this HQP is conserved quantity, and it's called usually energy as well. And for these even integer values, it has compact level sets. So if you start the system with some finite value of h, as any for this finite lattice, any q and p would give, then this value is conserved. And since it then remains in a compact set, you can use this to show that the Cauchy problem is well defined for any initial data. So somehow that's what I meant when I said that I want to start from a finite system, so that at this level, there is no question about having a well-defined system for any initial data. So let's, for the reasons which hopefully come clear soon, first look a little bit at the case, the easy solvable case, let's call it. It's also integrable when the lambda, the nonlinear coupling is 0. So this corresponds to a discrete wave equation. And as such, it can be solved by diagonalization. So taking Fourier transform, diagonalizing, then the PQ part gives eigenmodes. There are 2L of them. And the parameterization, standard parameterization, let's call it, is to give a parameter sigma to the two diagonal variables coming from Q and P, and the K corresponding to Fourier transform. The evolution of the eigenmodes, so this is my notation for the eigenmodes, is just a phase evolution, and it depends on the sigma and K, so it's non-trivial in the sense that it's not the same for each eigenmode. Omega here is a function which appears a lot afterwards. It depends on the harmonic evolution only. And in particular, notice this delta appearing here. So I've scaled, I dropped out one trivial scale, which could be an overall constant here, but after that I have a parameter delta left in my definition of the dispersion rules. Also here you can see why the delta has to have the values that we decide. One observation I want to make already at this stage is to note that when delta is small, the values you can take for this function omega, this only a small band of values which are possible. So this m minus here, which is corresponding to the minimum of the continuum function, just to remind you, so this k is in principle taking discrete values, but if you allow it to take all possible values on R, the minimum will be given by this number. And correspondingly, the maximum will be obtained when k is 1/2, given by that number. And if you compute the difference here, one realizes that this difference goes to 0 when delta goes to 0. So it depends on this parameter. So this delta I called previously as something which controls the harmonic coupling between the particles, but it also controls the width of this values of this dispersion relation can take. So let's turn on the interaction. In this case, as I said, the solutions are well defined. So let's now look at the corresponding definition of these phonon fields. So previously these were eigenmodes of the evolution, but now they are simply a linear combination of the Fourier transform of a certain solution. So we have initial data, we solve the system, we have Q and P, then we take this discrete Fourier transform to take the function, to obtain the function Q hat of K, for instance. And this is a particular combination which depends on the values of all this dispersion relation, and also on the parameter sigma, so it appears here. And the reason why this is a useful object to study also in the nonlinear case is that this gives us a very concrete form of perturbation theory, which one can start to iterate. So if lambda is 0, as you notice, this is simply corresponds or is compatible with the previous solution, explicit solution I wrote down. But now that we have turned on the nonlinear interactions, we find that there is this higher order polynomial in A term appearing for the evolution of A. In the following slides, I will use a shorthand notation where the minus sign in this definition corresponds to the case when I will drop the sign, and then taking the complex conjugate and recalling that the Q and P are real valued, one finds that the plus value is closely connected to the complex conjugate. So in principle, this can then be written also in terms of the field and this complex conjugate. Okay, so now I'm gradually going towards kinetic theory, and I wanted to recall a couple of assumptions which will be holding throughout all of the results we have here. First of them is that so far I've been considering arbitrary initially. So now we want to take it random, and in particular we want to have a randomness of a very special kind, namely they should be homogeneous, spatially homogeneous randomness, meaning that the distribution of initial data is invariant under translations on this discrete lattice. And one thing which I forgot to stress in the previous slides was that everything, when I talk about translations, addition, etc., all these operations are done periodically, meaning modular the size of the object. So you can think of a periodic boundary conditions. The definition in this case of a Wigner function, which will be appearing for the kinetic theory, can be given in terms of these A fields. Here is one version of it. Recall that this corresponds to plus minus using my previous sigma notation because of the star here. And I can also use the inverse Fourier transform to write this as something which maybe is more easy to understand why this typically would be a bounded function at least initially. So this is given if the correlations of the initial data decay fast enough. So these are correlations of the backwards transformed eigenmodes, normal modes. And then if these correlations decay fast enough, then this sum here yields this bounded by a constant uniformly in L. So that's sort of one condition, one explanation maybe why this is, it's a sign of one of the assumptions which we want to certainly make. So we would like to have that even though this depends on the L, this function, this particular, the initial data should be such that this would not have singularities, it should have actually a limit and L goes to infinity. Okay, so this explains that one. So that's really when t is 0, when we look at initial times, this is simply an assumption. We hope we are choosing a sequence of initial data for these lattices such that this limit exists. Now, this limit, of course, doesn't depend on the coupling, but when we turn on the dynamics, then it will be. So looking at the times here, they are scaled using the standard kinetic scaling. So tau is here a fixed number. We scale it with a coupling. Lambda was the unharmonic coupling. And not only we assume that when tau is 0, when that limit exists, it should exist also for finite values, at least some finite values, non-zero values as well. And just to mention for the later, when I talk about kinetic time scales, I mean times which have this property that when lambda is small, they are order lambda to the -2. And again, recalling what the meaning of these limits, first want to take the L to infinity, and after that, look at the coupling going to 0. Okay, and the conjecture continues, not only the limit exists, we also assume that it's assumed or it's supposed that the limit satisfies a nice evolution equation, and this would be an evolution equation very similar to wave turbulence. So spatially homogeneous wave turbulence satisfies an equation. This is very similar to the one which these chains, unharmonic chains should also satisfy. I didn't write this explicit form here. It will appear later. But just to mention, it's a nonlinear collision operator, and it will depend on the R. So I will write this down only for R equals 4, but there are similar forms which one can use for higher. And I'm not going to mention anything more about the assumptions you need to prove these things. I'm hoping to actually learn more about these on Wednesday. So let's skip the mathematical part here and go now to the topic of this talk. So that was kinetic theory of phonons. There is one particular observable motivated by this kinetic theory. There was a puzzle related to this, so let me already explain at this stage. When you look at the solutions, stationary states obtained from the solution to the kinetic equation, one finds that there are two conserved quantities. However, it was not, when you look at the microscopic evolution, one leads to the conjecture that there should be only one. And then this discrepancy, at least for myself, was the reason to start to look at the problem, what happens to this other conservation law, which appears in kinetic theory but shouldn't be there. This will be called phonon number observable. That's corresponding to this extra conservation law, if you want. And here's the link to the paper. Most of the results I'm going to talk about will appear, it can be found from this paper. which is also available in archive. And the main topic here will be to explain something which is called pre-thermalization. This is a word which was used in physics first. From a point of view of mathematician, I would prefer to call it quasi-thermalization. So thermalization is something where your state, usually it's stochastic, which would have a unique stationary state, for example. Here we don't have such luxury, so the stationary states are not unique, but at least they should be characterized by a couple of constant quantities. And in particular for the models we were talking about, there was also previous numerical evidence suggesting that there's only one constant quantity. So what happens here is that we will have a second quantity which is not conserved, but which changes on a very, very slow, long time scale. And this is why I would like to call it a quasi-thermalization. So while waiting for even numerically, while waiting for the system to thermalize properly, so to reach the final equilibrium state, one has to take into account that even though in the end there will be only one observable left, constant quantity left, for the very long time gap here, one has to consider the system as having two. So in that sense, I put here wrong equilibrium states. So they are wrong because they have the wrong number of conservation laws. And this will be the picture relating to the long observable conservation, extra conservation law in the models. So there will be three sort of windows in the time evolution of the system. So here I'm talking about time evolution of the state for this particular system. So the states are supposed to be sufficiently nice so that they for instance follow the kinetic theory. They are close enough to the kinetic theory predictions. So if this is the case, there will be first a window which is roughly order 1. During this window, the system will be following mainly the harmonic evolution, and this harmonic evolution will change. It will have lots of conservation laws, but it will change the initial state and make it as something which is more or less stationary with respect to at least in some sense stationary with respect to the harmonic evolution, the evolution without the nonlinearity. After a while, by this argument which was mentioned there, motivated by this argument, we would expect that if we wait for scales which are kinetic, that during these scales, kinetic time scales, most of the observables in the system, so again, most here means that sufficiently nice observables of the system should reach something looking like equilibrium. But now we will find one more quantity. So for most quantities, this plateau will not be there. So they will just simply follow the value they obtain after the kinetic evolution. But there will be at least one for which there will be change observed. And this will be observed on a much longer time scale. So this was kinetic, so that was -2. This scale here is lambda to 2p. And already at this stage, let me mention that why I say much longer. This p here is a function of this delta, and it will go to infinity when delta goes to 0. So if delta is sufficiently small, this p can be arbitrarily large. Okay, so let's now start to finally look at what this mystical quantity is. So I called it phonon number observable, and this is motivated by kinetic theory. Phonon number, this means you can think of this sort of intuitively, qualitatively, as an observable which measures the number of phonons. So this is the actual definition of the observable number of phonons with wave number k. It's a positive quantity, non-negative quantity, and it depends on this plus minus combinations of my A fields of this eigenmode fields before. The N0 observable, that will be the one which will give a rise, at least on the kinetic time scale, to the long evolving observables, is simply an integral of this individual phonon number density. So, sorry, there's an error, of course, here. this does not depend on k, it's integrated. Okay, well, looking at writing the Hamiltonian in this observables, this is the H was the original one. There was a harmonic part and the nonlinear perturbation, non-harmonic perturbation. The harmonic part can also be nicely written using the dispersion relation and this nk. It's very similar to the n0. It simply has different weight when we sum over the allowed k values here. Because of this reason, the Poisson bracket between these two guys is 0, which means in particular that if I would look at the evolution generated just by H0, the N0 would indeed be a conserved quantity. But when checking the full Poisson bracket with H, which is proportional, or which is given the time derivative, time change, rate of change of N0, according to the full evolution, this is 0, but that is non-zero. And in fact, one would expect this number to change. It cannot be stationary anyway. So N0 is not a conserved quantity, unlike H itself. So the procedure we are following here is motivated by originally from quantum mechanics. The idea here is to use this Hamiltonian structure in the problem and to find the change of variables. So change of these field variables Q and P, that's something which I put here in quotation marks, normalization of the field. So changing Q and P will change the A's. Then you look at an observable A, which has the same form as N0, but with this renormalized fields appearing there. Our aim is to do it in such a way that the rate, meaning the time derivative of this new observable A, is already lambda to the P, where P is the same number appearing in the previous line. It will turn out to be proportional to 1 over delta. So this goes to, in a very particular way, this goes to infinity when delta goes to 0. So delta was the harmonic coupling between 0 and 1/2. And just to mention that this is something special, because if I just would take I have lots and lots of these conserved quantities with respect to the original evolution then generated by H0, but in those cases, the time derivative would be expected to be order 1. So this should be just P should be 1 for those cases when I'm not looking at this particular observable A. But as I said, so if you are mathematicians, none of this has been proven, although this part is not too far from being provable. Okay, but let's look at the structure in a bit more detail, because this is one of those properties which just doesn't come out of nowhere. One has to really go into fine details of these evolution equations in order to understand what's happening. And the first thing, giving a sort of an idea of what's happening here, is to look at the kinetic equation in more detail. So my previous equation, where I didn't write down the collision term, should really, in fact, look like this. So after taking the L to infinity limit, this is the collision operator. It has two conservation laws here. There is a periodic conservation law with respect to the wave numbers, and there is a corresponding law with respect to the, let's call them energies. So these are dispersions relations of each of the participating waves. These two conditions have to be satisfied, but apart from that, there is a weight, which is not too bad. Apart from that, there is then the third order polynomial term appearing for the W. So that's the conjectured wave equation for this system. There are lots of terms with all kinds of signs here. However, for the particular omega, so this omega was determined by my harmonic interactions. This equation, in some sense, should be true for general class of harmonic interactions. But now I'm focusing on the nearest neighbor ones. So that was the square root of 1 minus cosine type of thing. And for those interactions, these two conditions are satisfied only for particular choices of sigma. So most sign combinations in this sum do not contribute, because these delta functions cannot be simultaneously satisfied. And using this fact, simplifying using symmetries, one arrives at something which looks easier. And in fact, this is an equation which can be numerically simulated. And the only thing I want to point out here is that due to the permutation invariance in the problem, it's possible to, for the remaining terms, which might be non-zero, to put them in order plus, plus, minus, minus. These were the signs from the previous slide, where we have more combinations appearing, but here only this particular one is remaining after all the symmetries. This equation, this collision term, this is not too far, at least from the point of view of structure, from this standard homogeneous Boltzmann equation, and in particular, it can be this usual entropy argument can be applied there. So there will be a function which satisfies an H theorem. This function will have a entropy production functional, and this which is non-negative, has a sign. And as zeros of this entropy production functional, one will then find that there can be only a two-parameter family of zeros of this type. And in fact, one can then check that each of these guys, as long as these functions are well defined, are stationary solutions of that equation. So this was one benefit from going to the kinetic theory. In these parameters W, it's actually possible to classify, assuming certain regularity, the stationary states of the system. So this W was roughly, if you want to think about it, it was roughly like the covariance of the local covariance of the system. So it has two parameters, and this is exactly reflecting the fact that this which I mentioned in the beginning, this mu0 shouldn't be there. It should be 0. So if one would do the analogous assumption and just suppose that we would thermalize to the usual Gibbs state with one constant quantity h, one would expect that when lambda goes to 0, this W should only have a form where only this beta appears. And indeed, this mu0, when it's non-zero, generates something which is not stationary with respect, it's not corresponding to the usual Gibbs states. Okay, so motivated by this, so as I said, this mu0 can be associated with the n0 observable. Let's look at what can we say about it. And the way to do that is to try to find canonical transformations, so changes of renormalizations of the field. And this methodology is motivated by steps used in KAM theory and semi-classical quantum mechanics in adiabatic expansions, for instance. So they are sort of the motivation for doing the steps, looking for the steps which we are doing here. But in particular, a direct motivation was an adaptation in this paper by Albanin, Teruk, Hu, and Hyphenes a while ago, where they used this to study pre-thermalization in quantum mechanics. So we are adapting this the technique to this particular classical case. Okay, and what's the point of this transformation? So you can make all kinds of transformations. We are in particular looking for those transformations. They will depend on this coupling lambda. So that when lambda is small, first of all, they should be close to n0, because that was the kinetic new observable. But we want to minimize the rate of change here. So as I sort of anticipated, we should get a non-trivial power of lambda for this renormalized observable. So let's do this in a little bit more detail. I apologize for all these fast steps written here, but just to summarize the way these things work, the main point about canonical transformations is that they can be written as something which is generated by Hamiltonian evolution. So this Poisson bracket generated by a function g now. So this g is like the h before. We are looking at the evolution generated by this function g. Poisson brackets will be defined as before, and this formal notation here it denotes the flow obtained from solving this Hamiltonian evolution equations generated by g. And the one nice thing about these are called canonical transformations is that they transform Poisson brackets, as you would hope. So a Poisson bracket transformed under this change of variables will become a Poisson bracket of the transformed observables. So in particular, this A, which I wrote before, this will be so we will choose a particular G. This A will be the canonical transformation of the N0 observable. So in particular, this sort of, at least on qualitative level, guarantees that when lambda goes to 0, we go back to the original N0. I will need another transformation, renormalization, and that's the renormalization of the generator of the dynamics. So H renormalized will be the same rule applied as here, but to the different direction. So these Hamiltonian flows, even though they are not always, I have nonlinear systems, so they might not exist for all times, but at least they have time invariance properties, so that it doesn't matter whether I go forward or backward in time. And the point here is that going to A, I go to the usual direction. When I renormalize the dynamics, I go backwards. And the reason for that is that with this definition, the time derivative of my renormalized observable. So this is now just using the original time evolution. This can be simplified because this Poisson bracket here between the A and H is obtained by using the flow of this G to the Poisson bracket between original N0 and the H renormalized. And the reason why this helps for us, so we are mainly actually now looking at ways of making this Poisson bracket small, partially because this N0 is such a nice observable. So N0 is something which is super nice. It has many nice properties. And this is the reason why which allows us to try to find G's such that this Poisson bracket would be a lower order lambda.
Sorry, Yanni, can I ask you a question?
Yeah, go ahead.
But this LG, I mean, the choice of the observable N0 is special. I mean, the LG is tailored to N0, or no, I should think of this LG as working as for a larger class of observables. So.
Okay, so we are tailoring LG so that we only study N0. So if I would have a different class of observables, I might not use exactly this choice. So it is tailored for N0 in our case. But the story, of course, doesn't matter. For the story, I mean, you could look at the larger class of observables and try to optimize with respect to this larger class. But in the following, I'm only optimizing with respect to N0.
Okay, thanks.
And maybe this will help a little bit. Here's more explicitly what's happening. So why am I saying I'm optimizing only N0? So this is the standard polynomial ansatz, where this P is a finite polynomial of things which are also polynomials. They are polynomials of A. And because of the special structure in this system, in particular, if I want to minimize this object here, I have a good idea what kind of polynomials I can use in my ansatz. And it turns out that, first of all, I should write them in K-space. They should have this one particular conservation law relating to the deltas appearing. And there should also be, in fact, what I also would like to have is a rule like that appearing in the definition. But in principle, you can think of this as just choosing an ansatz. So we choose GNs of this type, then combine them using this. And the point why this is not totally trivial is that this lambda is the same as that lambda. So looking at the first order, for example, the renormalized with this ansatz when P is greater than or equal to 1, or greater than 1 for this formula, this becomes something where I start to combine terms where one order lower from here combines with the term from there. And this is the extra property which allows to try to minimize these objects. And in particular, we are not minimizing them over everything, as I said, only with respect to brackets with N0. And this N0, as I said, is a nice observable. When acting on this kind of things, it removes all those combinations of sigma where the sum of the sigma is 0. That's something you need to work out. I mean, it's a computation. But the reason why this N0 is such a nice observable is that it actually cancels certain terms from this expansion directly. Okay, but otherwise, on this level, it's just the observation that when we do it using the same parameter here and here, we can exploit cancellations in these terms. And the first order correction, again, another thing which is maybe useful to point out that already at this stage, the first order correction depends only on G1. So this is consistent in the sense that every time you try to go further in this expansion, you will have the freedom of choosing the next term. So this will, at this stage, you will choose G1. If you not to go one step farther, you choose G2, depending on your choice of G1, etc. And just to give you an explicit idea of what's happening here, actually, this is also, there's one important thing about this. So in order to solve this equation by this type of ansatz, I have to think of this H0 acting on this polynomial. So this here is a Poisson bracket. So I use this notation because then it's obvious in which order I'm acting. But this here is just a Poisson bracket between G1 and H0. And H0 is a second order polynomial. And what it does here, it picks up a multiplicative factor. It doesn't do anything to the order of the polynomial. It simply multiplies this coefficient here by that factor. And in order to solve this equation, first of all, I have to cancel that factor. And this factor is the sum of the phases. This is something which already appeared in the kinetic theory as one of the constraints. But the difference here is that now these sigmas, unlike for the kinetic constraint, these now are exact opposite. So these are the guys where the sigmas do not add up to 0. But this correct, so I said so that I can define it like that, but only if none of this is 0. And one of the conditions for doing even this very first step is that this function omega-4 should not vanish if I look at the any combinations of this type. And this will appear in higher orders. So if I now simplify and go to higher orders, so here D is just counting how many omegas I will have, how many order polynomials I have. It will depend both on the order of the original interaction and how many times I have iterated. But it turns out that for this particular choice of omegas, there is a simplification. So it's enough to look at the case where I have a mismatch of these signs with a minimal amount. So if you carefully look at this, you observe that I think there are exactly 2 more pluses than minuses, I suspect. Anyway, the minimal amount, the D is always even. It also uses simplifications and permutation symmetries, etc., and the fact that this omega is a symmetric function. So we are requiring, in order to continue for this, in order to find these correctors Gn, we must have the property that this pair of equations cannot have solutions. And here I'm writing solutions not anymore on the L-dependent lattice. We want to look at the arbitrary L's or large L's. So in order for this Gn to be not only well-defined, but bounded in L, these solutions should not appear for any values of L, or at least not for any large values of L. And for this reason, let's just assume that they are true everywhere. And then by using continuity, etc., one will have the fact that there is a gap between values here and the 0. Okay, but the next step is something which I wanted to skip because it's lots of computations, essentially relying on the properties which we know about omega. In particular, now it will become crucial what the M- and M+ are. In our paper, in one of the appendices, the computations can be found. But just to summarize what happens, if I'm looking at the 4th order system, and here are the values of delta, so that was the harmonic coupling parameter, I can go up to order 2 if my delta is between this was the maximum value allowed and 0.3, so 3/10. If I look at 6, I cannot do even 2. I must remain on p = 1. So what this means, just on the level of the rates, is that this case is kinetic. So even though I was talking about pre-thermalization, this whole phenomena depends on the order of the perturbations as well. This power was the one. This is essentially no different from the other observables. When R is 6 and my delta is close to 1/2, there is no pre-thermalized observable, at least on the way we are looking at it. However, if I have R = 4, there will be one because this is already higher well, in principle, this could be also kinetic, but it turns out that that when you look at it, this will lead to something which is longer than kinetic. And when delta gets smaller, the p gets higher, but with a speed which is slightly different depending on the order. So when delta is small, for the fourth order perturbation, the p will be roughly 1 over the coupling delta. Again, one reason why the delta was a convenient choice. When r is 6, it has a factor of 1/2 extra, so increase is slightly slower, but still essentially 1 over delta is the dominant behavior for the increase of the p. And just to recall, so this p was the time derivative. It's the prefactor in front of the time derivative of the renormalized observable A. So when this is very large, even the observable doesn't change. The natural scale for the change of the observable is lambda to the p minus p. Okay, and up to now, these things I was mentioning, they sort of rely on well-used theories, and there is a hope of doing things rigorously. But in order to understand the numerical results, we need to go one step further. So the next step would be to really study thermalization, the final equilibration associated with these conserved quantities. And the results which I'm going to show here, first of all, I have to thank François Hufenes for the slides and also for the numerics, but they also based, the first slides results will be based on the work by Christian Mendelka. So now we are leaving mathematics even further behind, and now we are just using convenient hypotheses. That's the right way of looking at it. So first of all, for observables, this is in particular for the case when there is no pre-thermalization. If one accepts that we start from a rho 0, which when time evolves should go close to one of these Gibbs states, then we should have this property that so this is an assumption about large scale behavior. So T is large, and we are assuming that there is this stationary state rho 0 here, and we are looking at the corrections. So this rho 0 is invariant under the free evolution. So when lambda is 0, there is nothing to correct, but when the lambda is different from 0, we add a correction here. And we are trying to figure out what kind of corrections would lead to smallest numbers. And in this case, since this is the only observable we are interested in, we are minimizing this particular expression. I talk about minimizing, but in fact, there is a way of constructing it. So there is an ansatz for, let's call it ansatz. There's an ansatz what the F1 should look like. I didn't write it here, but it will appear, the answer will appear on the next slide. In particular, this object here will be relating to the usual current-current correlation functions. This was the something which we already discussed. And also, just to recall, now that I'm looking at this case, there was this one case when we don't even expect this to produce anything very particular, and that was the 6 and the large delta. In fact, I also forgot to mention, so all these results about delta, they will change if I change the dispersion relation. So everything I'm talking about when I'm mentioning p's depending on delta, I'm really only talking about nearest neighbor. If I change and add some next to nearest neighbor terms, everything can again change. So we are not making claims about different dispersion relations, only about the nearest neighbor. Okay, so if you now believe this idea that of this first picture about pre-thermalization. So the idea was that there is an order 1 scale when we follow something close to free evolution. Then there is the kinetic scale when the change, even the covariance will start to change. After that, if we now believe that this has will change on a much higher time scale, we should expect the system to approach something which is close to this particular measure with these two conserved quantities. And in fact, this form is consistent with the stationary solutions to the kinetic equation as well. But here's an example of the numerical simulation. So we start the system with some fairly arbitrary. In fact, W, form of W, we use random phases, and this square root is simply in order to make sure that the W corresponds to the absolute value of AK. The results here, this is the initial one, and this will be the result of the after the kinetic evolution. So you notice that this is of the same form, and by the conservation laws, actually, once this W is given the initial one, you can compute the values for beta and mu. So we in fact do know what this final value after the kinetic evolution should look like. That's the dotted line here. And when you do the comparison more carefully, so now the time is running. So this is 500 units, 1,000, 5,000, 10,000. There are microscopic dynamics and Boltzmann equation solutions appearing here. So these barely visible orange triangles here are obtained by taking this as initial data for the limiting kinetic equation, the homogeneous kinetic equation, and solving it numerically. And if we do that, indeed the W will follow the roughly the same as the kinetic one, and they will converge to something which is exactly the predicted kinetic equilibrium. So that's at 10,000 time units. However, as I said, we should not have this. This should not be the correct equilibrium of the system. Again, based on simply on the values of the constant quantities, this red line here, dashed dotted line, shows the W we would expect if the system would have only one conservation. And they are indeed quite far from each other, and there is no obvious evolution of the solution, the microscopic dynamic solution, towards this red line here. So the kinetic timescale here is roughly 1,000. So this is after roughly one kinetic time step. Okay, so to finish, let's look at now at the what happens after the when we go to these renormalized quantities. Here there are lots of simplifications and calculations. It's not so obvious anymore to compute the G1s and G2s for these models. The computations can be found in the paper. So I'm skipping all of those. Some of them are rather horrendous. But let's now make another ansatz how this pre-thermalized state should behave. And now we are moving to the, for this ansatz, we are moving to the renormalized variables, because it's easier, again, to keep this n0 here. So that's just a quadratic term. It's easier to think of the, or compute this, what happens here using the, this particular form. But if we suppose that the system, before relaxation of this n0, that the system would go close to one of these Gibbs states. So that's something which is proportional. And this is now the renormalized H. So we are in the new variables, so that's not renormalized, but H is. In these variables, as we pointed out, there is this lambda to the P appearing here. The J is a rate function, it's a flux rather than a current, but it has mean 0, computation again. And now if you follow this idea, same ideology as for the first case, one ends up with a prediction, let's say, or a hypothesis, that the final large time change of n0, the rate of change, should follow, when lambda is going to be very small, should follow something which is almost explicitly computable. The reason why this is explicitly computable is that these j's can be computed up to the 0th order. So the lowest order term for the j can be computed. And this expectation here occurs over the Gaussian measure. So there is no tilde anymore here. The tilde is somehow contributing here. So taking this, I've thought of as the dominant term. Notice that this indeed now has doubled the order here, and the next one could be only one order smaller correction. Now we can have not only a prediction about the scaling of the rate. Now there's a totally explicit prediction even for the prefactors. So this will depend on the mu and beta, which were the parameters for the first state. So they will depend on these parameters. But other than that, everything here is in principle computable as a number. And now we can compare this number to numerical simulations. And for the numerical simulations, they are done similarly as to the previous one, which was done by Christian Mendel. Now the difference is that we start from initial data, which is supposed to be already stationary. I think that's the difference. And there will be a small, so this picture here is a blow up of this particular one. So it's the first half of this picture, I think. So in the beginning, there will be a apparently big jump here in this observable. So that's the N0, which should be, it is extensor, it's proportional to L. So this is a finite number, as you see. There will be a jump, and this should correspond to this order 1 thermalization point. So we just ignore that. But after that, it seems to follow sort of fairly nice dissipation rate, and this rate here is the one which is computed in the following picture. So many simulations are done with different deltas and R's, and this gamma appearing as a blue dot is something which is computed from this rate here. The lattice size is 1000. So if you want to complain this is too small, you are allowed to do that. Okay, but let's look at the results. So the size is the same, only the R and delta are being varied. So this was the case. Let's first start with a case which should not have pre-thermalization. And indeed, the gamma here is something. So this is rate, so it's 1 over the time derivative. Is something which should be on the kinetic timescale. And indeed, it seems to be compatible. So I should stress here that this orange line here is not a fit. It's a linear line with this particular numerical constant here. And many simulations are done first with keeping the beta fixed and making lambda small. So we would expect that this result becomes better and better when lambda goes to 0, and indeed that seems to be the case. But this is not too surprising in some sense. It's just confirming kinetic theory if you want. Similarly, we can check what happens if we vary instead of lambda. We keep lambda smaller but vary beta. Again, the fit is not too bad. But let's go now to the case which is not kinetic. So this is closer to the first simulation by Christian Mendel. So his simulation actually had delta which is 0.25. He was never able to see the final thermalization, and now we can understand why. I think 0.25 already has powers delta to minus 12 or delta to minus 16. So this is just too small. So the time scales in which you would see things with delta to 0.25, they were just out of reach. So this is the reason why we choose, first of all, a bigger delta, because then we know that the P is larger. In particular here, it's the first non-trivial one. So this is non-kinetic, but it's only as appearing as the next step. So it's lambda to the 4 instead of lambda squared. Numerical constant is bigger, and that's unfortunate. But like before, similar features appear. So the thermalization as a function of lambda, thermalization rate as a function of lambda appears to follow the predicted value when lambda goes to small values. So that is certainly fitting what we were computing in this heuristic formula. The next one, let's see, that's again the same, but varying beta. But finally, let's go to the case which is close to Christian's simulations. This is 0.28. I think this is above. So the P increases like 1 over delta, and when delta gets small enough, even small changes in delta can change P quite a lot. And the difference between 25 and 28 was, I guess, the maximal we could do. So this 28 still had the P, which I think it was still in the range of 4. But now the pre-factor has increased, and indeed the fit is no longer so great. This could be produced by the factor of the 6 here. So I would just like to recall, so here you see that the fit is not so great. So the orange one is the predicted one by the first formula, and this green one is a fit. Now this one, it has slightly different power, very different prefactors, but this could be caused, for instance, by the fact that there are correction terms, let's say of order lambda to the 6 with high prefactors. This type of phenomena would need a very small lambdas for this dominant term to become really dominant. You can also understand it by the result that the dominant term is lambda to the 2p, while the correction could be lambda to the 2p plus 1 or 2. We don't actually know which one, truth be told. But in any case, when p is large, it's almost the same. And therefore, it's not surprising that they start to interfere. So presumably, this could be this discrepancy here could be caused by the interference of the higher order terms. And indeed, if you look at the difference here, it sort of very slightly starts to get smaller when lambda gets smaller here. But of course, already 10 to the minus 4 is fairly bad for the numerics. I think there is a next the same one with the similar conclusions. So what are the open problems? As you probably guessed, quite a lot if you are a mathematician. First of all, rigorous justification of this relaxation scheme. I mean, that's something where I think even things could be learned, in the sense that one should work there in order to understand what's really going on. It also starts from an assumption which sounds physically very appealing, that we are close to this pre-thermalized state. But again, of course, how on earth would you prove that? That the time evolution in the kinetic time would lead you close to the pre-thermalized state. Again, things which need lots and lots of clarification. So certainly I don't view this as a very easy problem. Something which might be easier, which we have already started to work with Alexis Voxema, a PhD student of mine, is to look at inhomogeneous case. There the questions will be different. The problems will be different, let's say. The first problem is that the kinetic theory gets more complicated. There could be a Vlasa-Poisson term appearing. Again, proofs and proper assumptions are something we are working on, but this could be tight, these two steps. So in order to understand, to have better control over the kinetic time scale could be necessary before you can really do control over the relaxation scheme. Okay, but I think my time is up. I thank you very much for your attention, and let me stop the sharing.
Okay, so thank you very much, Yanni, for the very clear and nice talk. Are there any questions? From online participants, I would just suggest that you unmute yourself and directly ask. Yes.
So maybe one. When you were discussing your renormalization procedure, you had this non-resonance condition, right? That somehow you kept going until you had these zeros. But I mean, that's true that this. So I mean, the question is, what happens if this, instead of having zero, you have something which is very small, in particular, that can go to zero as L goes to infinity? That doesn't create a problem?
Obviously. So yeah, that was the reason why you have to make sure that that the k values have to vary over not over the lambda star, but the entire torus. So this is the only reason which guarantees that that this 1 over omega terms which come in the correctors, they always appear there, as you probably already noticed. So that in order for them not to spoil this story, it is necessary that we check the condition, the non-resonance condition, let's say, for all k. But this is enough to guarantee that the gap exists. So for the conditions I'm writing down, the continuity will guarantee that there will be some L independent value for the 1 over bound for 1 over omega.
Okay. And the second question, if I may, so is in what sense? I mean, how is this method different from, let's say, usual KAM theory, right?
I'm not sure. I think not, in no way. So I apologize for not giving the usual KAM references and things like that. I just wanted to keep this list of references short, but I think it's very close to it. I am not in the KAM result. I don't know if you want to. Do you have this phenomena that you have to stop at a finite order? This is maybe a difference. Maybe the goal is slightly different, but the method, I believe, is the same.
Okay, thanks.
This will be one question from the online.
Question for Yanni.
Hello, Herbert.
Yes, hello, Yanni. Very nice talk. I was just curious in terms of your simulations. I mean, over how many initial data do you have to average in order to see such good sort of results?
I think quite a lot. Unfortunately, I don't have the numbers. The answer is a lot. So this is not something you will see when you look at samples. So you must average. In particular, this translation invariance, the spatial translation invariance, you must average enough for this to appear. Sorry, I don't remember the numbers, but it's a lot. I think that's my main obstacle here.
Thank you.
Other questions? Maybe while you're thinking, if there are others, I will ask one about your last comment about the appearance of a glass of Poisson term if you consider inhomogeneous data. Can you give a little bit of intuition why you expect? So first of all, then you mean like a nonlinear transport term appearing?
Yeah, so this is something you can see if you look at the I have slides for that, but unfortunately not available right away. So if you look at the let's say formal expansion, just using the formula, the exact formula for the time derivative of A. If you do that, the order lambda term for inhomogeneous systems, assuming you believe certain uniformity, which is difficult to check, will produce a term which is totally analogous to the standard class of Poisson. So it is, there will be two terms appearing then. There is an order 1 term which is corresponding to the transport. This is the usual transport type of term, but an order lambda term corresponding to something like class of Poisson. It's a nonlinear term because it's a self-consistent potential term, if you know what I'm talking about. But in any case, this can be motivated if you believe certain differentiability assumption quite easily. The main question for myself is that is this correct? I mean, the motivation is not very strong. These differentiability assumptions, they don't look very, they are very difficult to control. In particular, it's difficult to control that they are preserved by the dynamics. So I think that some work is needed, and that's why I didn't even want to write it down. So there is an ansatz or a hypothesis what it should look like, but I don't know if it's correct.
So then you mean that they coexist, so the glass of Poisson term and the Boltzmann-like
they should actually interact, and so it could even be that part of this sort of well, anyway. So it's the order lambda. It is lower order, so it's a faster term than the kinetic term, and the interaction between these two is also creating trouble. So that's the reason why I didn't really want to. Let me not write any equations down. I don't know if they are correct. So that's the main reason. But something happens there. That's clear. So that much I know.
Thank you very much.
So the spatial inhomogeneity. This is the reason why the glass of Poisson term is not there. It's 0 for spatially homogeneous states, and this is one of the reasons why I insisted really on the spatial homogeneity throughout the talk.
Thank you. Are there other questions? So here it doesn't see the face. Okay, then thank you again, Yanni.
Thank you very much.
Set up the break.